the big question where we want to leverage the power of having a formula for revenue, and not just individual data points, is how can I take this formula for revenue and turn it into a formula for the rate of change, the instantaneous rate of change of the revenue instead. So what are we talking about? First of all, notation-wise, we're going to call that instantaneous rate of change R prime of x. So this little apostrophe up here. When we read it in English, we say the word prime. It's like Optimus Prime. I don't know. It just has this meaning that this is not R that we're about to write down. It's something else related to R. And if we want to be fancy, and if we want to really sort of spell out what R prime of x is, we call it, alternatively, the instantaneous rate of change. That's the mouthful of a way to say what this is. The rate of change of R at x. But more commonly, because that's way too many words to describe one concept, we can also think of it as a slope. But the slope of what? When we talked about average rates of change, the slope that we talked about was the slope of this line joining 2 points on the graph. It's a line that we call, in mathematics, we call it a secant line. It joins 1 point on the graph to another point on the graph. 1 point to another point. But when we're talking about an instantaneous rate of change, we don't have 2 different points. We only have a single point. So the line that we're finding the slope of doesn't connect 2 different points on the graph. Instead, it just sort of cruises by and touches 1 point on the graph. That's the line which, when we find the instantaneous rate of change, we're really finding the slope of. And someone remind me what this line is called. It starts with a T. Tangent, exactly. So when someone says that they're going off on a tangent, which I do way more often than I should, when someone says they're going off on a tangent, it has that connotation that what's really happening is we're going along in some prescribed path, but then at some point we just sort of leave the tracks and we go off in a different direction. That when we first leave the tracks, we're going in the right direction, but then we keep going in that direction and the tracks curve away from us. That's kind of the picture of what a tangent line looks like. So going off on a tangent really does kind of mean, starting off good and then sort of getting off track while the track leaves us behind. So when we say instantaneous rate of change, another way we can say that graphically and visually is it's the slope of a tangent line. But that all is still a mouthful. It's still too many words. Instantaneous rate of change is putting the focus on what's numerical. So this is a manifestation in numbers of this quantity that we're computing. When we say the slope of a tangent line, that's a manifestation in pictures of what we're talking about. But what we really, really want is to leverage the power of formula. And when we find a formula for this, we're going to call that formula the derivative. So all of these 3 things are synonymous. Which one of these phrases we use might depend on what exactly we're trying to accomplish. But keep in mind, whenever you see one of them, you can, without a second thought, think of the others. So derivative, slope of a tangent line, instantaneous rate of change. All of these things mean the same thing, even though they use different words. And so the burden of proof on us is to figure out a process by which we can turn a formula for our original quantity, which is the revenue in this case, and discover a formula for its derivative, R prime of x. So let's talk about what that formula is. We'll come back to that slide in just a moment. For the purposes of our course, this being applied calculus for business, I want the focus to be on what the derivative means, what the derivative can do for us. And so we're going to try to the extent possible not to get lost in the computations of a huge petting zoo worth of different kinds of functions in this class. We're going to focus on one type of function for our derivatives. And because it's a very flexible type of function, we can do a lot with it. That function type are the powers of x. And when we combine powers of x together, we get polynomial functions. So these are the kinds of functions that we're mostly concerned with. So example, x squared. So what we can do is come up with a rule. I like to call it a basic move. It's like one tool in your toolbox, but this is a very common tool you're going to reach for a lot. It's like what the hammer is to the carpenter. This basic move is to somebody doing differential calculus with polynomial functions. This is going to be what you reach for when you take every derivative that you take in our course. And the basic move is this. To turn a function, a formula for a function like x squared, let's call it f of x equals x squared, into a formula for the derivative. So now the derivative we'll call again f prime of x, which is the slope of the tangent line, which is the average rate of change, instantaneous rate of change. The basic move has two steps to it. And the more practice that you get with these two steps, the better dancer you will become. The first step in taking the derivative of a power of x is to look at the power. The exponent in particular. In this example, that's 2. And the step is, I'm going to multiply my expression by that exponent. So that's the first thing we'll do. Multiply by exponent. So what that'll do for us is it'll turn x squared that we had before into, well, according to the first step, what I'm going to do, and here's how I usually diagram it, I'm just going to take this 2 and kind of go like this with it. That's my first step. Multiply by the exponent. If it wasn't a 2 up there, if it was a 5, then I would multiply by 5 out front. If it was a negative 12.5, I would multiply by negative 12.5. Whatever that exponent is, multiply by it, and that's the first step in this basic dance move. Second step is equally quick and essential. In the second step, we look at the exponent again, but we do something different with it. So exponent is still up here. What I'm going to do in my second step is decrease that exponent. And the amount by which I decrease it is always the same in taking a derivative. I'm going to decrease that exponent by 1. So in my second step, I'm going to take what used to be a 2, subtract 1 from it, thereby getting 1. So there is an application of our basic move. That if my original function is f of x equals x squared, if this tells me the value of some quantity, then this function, f prime of x equals 2x, will tell me the derivative, the rate of change, instantaneous rate of change, or the slope of a tangent line to that function. And all we need in order to make that happen is this basic move to find the derivative of a power of x. So it turns x squared into 2x. Let's play around with it some more. Let's say we start with, I don't know, x to the 15th. What would I get as my derivative for x to the 15th?
15x to the 14th.
15x to the 14th, yeah. Trying to go at a pace that doesn't insult your intelligence, because as long as we got these basic examples down, now let's ratchet it up a little bit. Okay? This basic move for the powers of x is more flexible than it might appear, because there are a lot of expressions in algebra that are secretly powers of x, but don't look like it when you first see them on the page. X to the 15th is pretty obvious that it's a power of x. But there are other powers of x that are kind of hiding. Let's suppose I have something like this. F of x equals 1 over x to the 7th. I cannot use the basic move yet to take the derivative of this expression, because it is not just a power of x. It's something else happening to a power of x. So before I can do any calculus, I've got to do algebra. I've got a little mantra that I tell people, especially in math services, but anyone I talk to about calculus, the mantra is algebra before calculus, ABC. Why? Because when you do calculus, you should do it with as simple of an expression as possible. So do whatever algebra you have to do to simplify first, before you think about doing any steps that we would consider calculus, such as this basic move to take the derivative. So our first step before the basic move, maybe step 0, is to simplify your expression into a power of x. Into x raised to some power. So, what power of x is 1 over x to the 7th really equal to? X to the negative 7. Exactly. And this is why there's all those properties of exponents that you learn in algebra and pre-calculus, is that now they're going to come in handy to let us rewrite that thing as a single power of x. And now that it's a single power of x, the basic move applies. And what is the derivative of x to the minus 7 according to the basic rule? Very good. Negative 7x to the negative 8. And I am totally happy with that, and I've totally screwed up my colors. Negative 7 in red, x to the negative 8. All right, so that was one example of a power in disguise. Here's another example of a power in disguise.
Hi, we have a question. What app are you using?
But that's the thing. This isn't algebra. This is calculus. No, you don't, because you just did this flawlessly. So, my point is that this basic move is the building block of every differential calculus, every derivative problem that we do. This is the building block. So the better you are, the more practiced you are at this. When this becomes an instinct for you, you've won 90% of the battle. I believe. And how do you make something an instinct? You do it over and over again, right? Until it becomes second nature. So that's the first thing I want to make sure we get a chance to get practice on, is this basic move. Now,